Boom. Okay, so we started talking about coverage testing last time. Can anyone remind me, what's this coverage testing stuff about? Why do we need coverage testing?
So you have a certain amount of confidence in how much of your system works?
I love it. I love it. Your name again?
Corey?
Corey. Thank you, Corey. Yeah. So we need a certain measure of confidence about our system and that it's working, right? And we can't test exhaustively. We can't test everything. That's not possible. It's combinatorially impossible. You can't possibly try all possible user inputs or what have you. So you have to focus your tests. And I talked earlier about focusing on high-risk areas and so on. But one of the ways that it's fruitful to focus is making sure you have a certain degree of thoroughness in your tests, right? To cover a certain breadth of possibilities in your tests. After all, if there are areas of your program which your tests have never reached, it's hard to have much confidence that it's going to behave correctly there. So the idea behind coverage broadly is to achieve a certain breadth of execution of your program. Now, there's going to be a lot of different ways we can make concrete the sense of coverage, okay? So we talked last time about state-based coverage, transition coverage, and today we're going to talk about prime paths and, if time allows, logic coverage as well. And I emphasize that the sort of reasoning that goes on here can be undertaken at the overall system level, where you sort of characterize your system as going between pages or between screens of an app or between functional states, like here. Or it could be undertaken at the level of particular pieces of code, specific items within the system, and algorithms within those. I remember way back in the day, when I was a young man, seeing one of the software engineers in the Excel team at Microsoft, who I was working with, doing coverage testing over some of the core functionality that every one of you have used if you've done things in Excel. And he was trying to make sure that every branch was covered by at least one test as part of his testing, to make sure this core algorithm to basically do a topological sort and update things on the spreadsheet based on changed values was operating correctly. So, last time, mostly with high-level examples, I talked about coverage at the state level, and I noted that it's a starting point. At least you prevent the most hideous embarrassments if you cover every state, but it's awfully weak. It's awfully weak because there are certain particular contexts, certain particular transitions which aren't covered, right? So in this case, we hit every state here, but we only had one type of cancellation. We never actually investigated cancellation if a refund was required. So by covering only the states, it was kind of limited. I think this is another case of kind of a workflow where you could do testing on workflow. But it's worth emphasizing this sort of reasoning can go on at the level of code. So you can have a fragment of code within your system and map it to an abstract characterization that hides a lot of details, hence abstract, but it brings out some of the most salient ones. And these nodes here are what are termed basic blocks. For those in the compiler course, how many people are in the compiler course here? Okay, I salute you. That is on. That is a good course for an aspiring software engineer. If you really want to see how real complexity can be handled, and in the context of needing flexibility, reconfigurability, extensibility, what have you, compilers are a great example. Okay. So, what's that?
I said I feel that you don't need the whole computer science course because like it's everything covered in this class.
Yeah. It covers. It's kind of a grand tour of.
Every course.
Yeah, that's right. That's right. Language theory, issues having to do with regular expressions and aspects of complexity theory and OFUN notation, issues having to do with optimization and performance, software engineering. It's right. It's kind of a holographic thing. You see all of computer science and compilers. Okay, so here, these nodes are basic blocks. They're contiguous straight line bits of code. There's no branches within these. Okay, and in this case, the code is particularly simple. N0 reflects some basic block before it. In N1, we have just these two statements here, and N2 is whatever's after it. And over here on the right-hand side, we have similar basic blocks here. And these control flow lines indicate where the system goes. So following N2, for example, it loops back to N1. So following the end of this, it will loop back and check if that condition is true. If it's still true, it will continue to iterate here. Otherwise, it will go that way. So this is a control flow graph. It's called CFG, which depicts the flow of a system. And the same basic mechanism we can use to test things here, we can do here. So if you have a core algorithm that you're trying to test, you can map it in a similar way to nodes and transitions. Okay, so last time I characterized key steps, specific steps in coverage. What are these steps? Number one, we identify the set of things we need to cover. Give me a meaning of what I mean by things. I'm trying to see if you're following my transition from general comments to the specifics here. So what are the things we might need to cover? What would the things be for state-based coverage? I'm not asking a trick question. For state-based coverage, the things we try to cover are state. For transition-based coverage, they are transitions. For for prime path-based coverage, as we'll see, they are prime paths. Okay, I'll be defining those. Okay, so you identify, you enumerate them, you figure out what those are. Typically straightforward from your diagram. Then you figure out a set of paths through the system from some start to some viable final state that will cover these things. Now these are abstract paths. We need to go here, we need to cover this. It's kind of like going back to this guy here. I might say, okay, I need to cover all these states. So I need some state that will confiscate the card, right? Suppose I wanted to do state-based coverage. So I would, say I need a flow that goes, for the sake of my internet viewers, I'll do it this way. It goes like this, and maybe I'll do one invalid pin try, and then, I haven't reached that. Yes, invalid pin try. It will go around 2, 3. It gets confiscated. All right. So that would be a path, an abstract path that would get me to confiscate card. Another way we would go with a card that's expired, and it would suck it in. Another way, if I needed to get through eject card, I could go all these ways and come down and go like this. Come down with invalid account. Or I could come down with insufficient funds. So if I wanted to achieve state coverage here, I could do so with a modest number of transitions. Another one might be entirely correct. I did achieve state coverage. Those are abstract paths. I haven't yet gone into how I realize them, how I make them happen. Finally, and this is the key thing, you need to develop a set of concrete test cases. Look, at the end of the road, folks, at the end of the day, when the rubber meets the road, you're going to need to test your system with concrete inputs. You're going to need to press these keys, click on this, go one back, etc. You have to come up with a test case. So one of the teams, I'm trying to remember which it was. is it team 1? I think it was team 2. I can't remember for sure off the top of my head. One of the teams had a test that was a UI-based test. Click on this, click on that. It was actually putting it through its paces programmatically. That was your team, yeah, team 1. So that's an example of a concrete test, right? You're clicking on this, you're doing that, and then you're seeing if the correct result comes. That's what we're trying to produce here. But we're trying to produce those test cases to match these abstract scenarios, these paths through the code. Okay. Now these test cases may exercise additional paths, and that's fine. But these are the actual take-homes. These are the things you perform to realize this. Okay. Coverage techniques will let you derive legal paths through the program from start to finish that will exercise this functionality. And then we'll have a set of test cases. Okay, so here's a little example. Here's some C code. Right? Here's some C code that does CGI decoding. So, here we have a URL, and it will turn it from an encoded form, where pluses are used to indicate spaces and percent hex characters become a certain byte, special high ASCII character, or what have you. It's going to turn into text. So here's the code. Here's some C code. Go test it. I want you to test this thing and achieve a certain level of coverage. Okay, so let's think about how that's done. We could break this into a graph. I want you to watch the mapping here. Right? Here's this C code. And take a look, for example, at this while loop, right? We initialize some variables, and then we engage in a while loop, and we have various cases here. Case 1, case 2. Case 1 is we have a plus. Case 2 involves a percent sign with a hex value, presumably following it. So watch that. Watch this. So we're going to transform it. Here's this initial header. Here's this while loop. Here's this case 1, right? Here's the initial part of this this loop header. Okay? Here. So we have mapped this code into a control flow graph. Right? We've mapped it into a graph with nodes and edges between them. Okay. Now, suppose with this graph we want to achieve a certain level of coverage. Suppose we want to achieve, for example, state coverage. How would we achieve this, given this sort of rubric of which I've shared, this general sort of depiction as to what you need to figure out? What do you need to do here? So we've done the first step already. We've figured out, we've done the 0th step. We figured out how to represent this as a control flow graph. What do we need to do next? Suppose we want to have states. What do we need to do? Get state coverage. So to be very clear, we want to hit each of these states. How are we going to achieve that? Sanity check. What's going to come out of this whole exercise? What am I going to get out? I'm trying to cover these states. What am I going to get out of it? Indeed. That bad a week, eh? You should see what mine was like. Okay, so what are we going to get out? I mean, we want to test this. We want to hit all states. What do we need to do? What do we need to specify to hit all states? We need to specify an input that will hit all states. Specifically, an encoded string that's going to be decoded. That's what the job of this code is. The job of this code is to take an encoded string and turn it into a decoded string, to decode it, to turn it into a string where the pluses have been replaced by spaces, etc. So what we want from this code and a test plan is some specific inputs that are going to do what? We're trying to cleverly pick specific inputs that will achieve what?
Hit every node.
they'll hit every node here. They will hit every node. That's what we want. We need a set of specific inputs. We want to feed this thing from our test harness, call it CGI decode with this string, and CGI decode with that string, and do that so that collectively we hit all these statements. In Cobertura, or your favorite C coverage tool, will give 100% coverage in terms of the nodes, in terms of the statements. 100% coverage. So that's what we want. How are we going to figure that out? How are we going to do that? Well, given the rubric I said earlier, we want to identify the states. Okay, the states are just shown in front of us. And then we need to figure out what? What was the rule? What was after the states? What do you need to do next? Figure out the abstract paths, right? We need to figure out the paths through here that they'll go from start to finish. That collectively will cover all these states. And then we're going to figure out the particular inputs that will exercise those paths. Okay, so let's do this. So give me some ways that I could cover all these states. Give me a legal path through this program that will cover a bunch of them. First one is always typically easy. Give me one that will cover a bunch of these states. What's an abstract path from start to finish?
You mean like an input?
Yeah. Oh, no, it's not yet an input. It's a path from start to finish that's going to cover all of these guys. This is the finish here. This is just a loop here. And the finish. So it's going to be a path through these. The path is going to go something like A, B, C, D, F, H, L, B, M, something like that. So give me a path that will cover a bunch of these. Now, if you did a recording, you could play it back for me.
A, B, C, E.
Okay, so let's trace this. Is that Nobleman?
Yeah.
Good job. A, B, C, E,
L.
L,
It's B.
B,
C.
okay, C,
E.
D,
F.
D, F,
L again.
L, okay,
That to B.
back to B,
Then M.
then M. Okay, so Nobleman's path is a very good one. It covered a great many of these, right? It didn't cover all. It didn't reach G, I think,
You
right?
could just go through it one more time and then go on the right side of that.
You could. Or you could come up, you could use, so yes, you could. Or you could have another path that will exercise purely this path here,
Yeah.
and then leave, and collectively between those two paths, those two abstract paths, you'd have covered all these states. Do you get that? Okay. Now we're still not done. Far from it. We're not done yet. I mean, coming up with abstract paths, that's great. We'll do this and we'll do that. That's all fine and good. But at the end of the day, when the rubber meets the road, you have to give it some particular input. You can't say, cover these nodes. No, make this path. It's not going to listen to you, especially if you speak in that voice. So what are we going to have to do? We're going to have to we're going to have to figure out some particular input that will follow Nobleman's paths, for example. Right? So we need a particular input. Now, this is not totally trivial. Okay, we're going to have to figure out a way to make it go the way Nobleman described. So let's try to do that. So you folks probably remember it better than I. After all, you enjoy the many virtues of youth. Okay? A, B, C, D, and then I think, Nobleman, you said F, right? Yeah. A memorable letter to students. So what we need to do, can anyone tell me, what would I need to do? Just speaking in intuitive terms, how would I get to F? I could feed it a string that begins with what? Like, what's the first character of the string?
Percent.
Okay, so it needs to be percent, right? Because if it's plus, they go that way. If it's some other letter, it'll go this way but go that way, right? But if it's percent, it'll go, excuse me, so the percent will go this way, excuse me. Percent will go that way. So you need a letter that's not percent and not plus, right? In order to kind of get it to go to F, you don't want to give it a plus or percent, right? Okay, so you get it down here, so it's like some letter, right? A would do. B would also do. The point is, either of those will get us down this way. Okay, then we come up, and then what's going to happen, Nobleman? Now you went back to C again, right? So it needs to be some other letter here. We're not ending the string, okay? And this next time you went to E, didn't you? Was that right?
Yeah.
You went to E? Yeah, you went to E. So this time, what do we need? A plus sign, right? That's how we're going to get over to true. It needs this thing equals that needs to be true. So we have to go this way, right? And then what? Okay, we come down to L, and then what happened?
Increment.
Okay, so it increments it at the next point in the string, and then what happened now?
The string is done.
The string was done, so this has to be, so if you gave it a string, give me, and then it finished, right? So give me one string that would satisfy that. That path could be exercised, but could be realized by what string? Give me an example string.
Plus.
A plus, a fine sequence of characters and a fine grade, right? Okay, so that's good. Give me another sequence that could also exercise that.
B plus.
B plus, yes. A perfectly respectable set of characters. Okay, B plus. So that would also have satisfied it. They would realize Nobleman's path. Now, if we wanted to go this other, have an additional path that went through G, give me a string that would go through G. Remember, we also haven't gotten to either H or I, right? We haven't hit H or I, right? Is that right? Yeah. We didn't get to either of these because we went through these, but we didn't get to H or I. Okay, so let's finish the node coverage here, right? The state coverage. Now we need to cover these states. We haven't yet reached these states, right? How are we going to get it to do that? Well, given a path, give me an abstract path that will cover these states.
Percent.
Well, okay, that's a concrete test
Oh,
case.
path.
But an abstract path. Just read off like A, B.
C, D, E, or A, B, C, D, G, H, L, B, C, D, G, I,
Okay, good. L,
B, M.
M. Yeah, LBM. So remember, it has to go from start to finish. That's a need for it, right? Okay. So now a concrete test case that will exercise that. How are we going to get it to do that? How are we going to get it to take that path? Okay, so start telling me what might be in this string to get it to do that.
Percent.
Okay, so percent would be the first one, so it will come down here. It's not plus. It'll come here. A test if it's equal to percent. It comes here, and then you said H first, Evan?
Yeah.
Yeah. Okay, so H and okay, okay. So if we're going into H, what does this need to have? There's a branch here. So what has to be after the percent sign? Yeah, I know. I don't like this code either. Okay, but what is this testing? Do you think? Okay, basically, are these legal hex values? If either of these is not a legal hex value, either the hex digit, if either the first or the second one after the percent is not from 0 to 9 and A through F, then if either one is not, if it's like percent Z, ZZ, then it will go this way, right? Okay, so give me, tell me, so we have percent, that's a good start, and then what? If we're gonna get to H, we need percent.
Z.
Z will take it this way, because if either, Z will be an illegal value, therefore digit high will be negative, or digit low will be negative, and therefore it will go that way.
Percent A.
Percent A, okay, and what's after A? Another hex digit, right?
Yeah.
So it goes this way. So neither of these are illegal. So A, percent A1, right? A1. It'll go this way, and then come down here. Okay, percent A1, so that's a good start. Now we need to get over here. So what are we going to do?
Percent Z.
Okay, percent ZZ will do it, exactly. And it'll come down here, and it'll actually ignore the ZZs. And continue on. Now, I see one very uncomfortable thing here, which I don't like showing you this code. It's a good example, but it's bad code. Why is it bad code? What would happen if I had percent at the end of the string? Yeah, you could get a null pointer exception. These guys would go off the map, like go off the end of the string, and they could trigger a seg fault. Did you ever encounter seg faults? You're not innocent of them. Okay. Well, my apologies. This could trigger a seg fault because it does something off the end of the heap, and the earthquakes and bad things happen. Yeah. So this should really be testing. Is this within bounds still? Of the string. In any case, if you go off that way, so yes, the string you mentioned is correct. Percent A1, percent ZZ, it's just going to ignore the ZZ. It comes back here and it finishes. Okay, so we have two test cases. And in general, we can exercise this with one much more complex test case or a couple non-complex test cases. So, ladies and gentlemen, here are some test cases. Now, the way this is arranged, these are actually test suites. So this top one will by itself test all those states. It'll reach all those states. This bottom one, it's just a single string. It'll reach all those states too. Huh? Okay. I think there's a bug in that. This will not, percent 9K, there's no way this is going to reach H. This guy, I don't see how that's going to reach. There must be a mistake. If this were 9A instead of 9K, it would reach it. But these are concrete test cases, and you're seeking concrete test cases that within each suite collectively cover all those states. So let's go back through the descriptions here. Here, we identify a set of things we need to cover, the states. We develop a set of abstract scenarios that will get us there, these paths, that will collectively cover all of these. They'll cover all these things we need to cover. Maybe they're states, maybe they're transitions. We need to cover them, and we do so with these abstract scenarios, these paths. And then we develop concrete test cases, inputs, that will exercise those paths, thereby covering all the things. Does that make sense? Okay, so my challenge for you, as you enter your breaks, is to think about how you would come up with concrete test cases that will achieve at least transition coverage for your projects. The project gave me, to my delight, a depiction of states and transitions. I think every project had that, although I did not come across them in last night's perusings consistently. But that's a great start. Envisioning your system as a set of transitions between pages or between functional states of the system, that's excellent. Great start. The next task is to come up with test cases that are going to exercise all the transitions there. What is the user going to have to do? What should they enter here? What should they enter there in order for it to come and cross all the transitions? That's my question to you. That is what I'd like to see. That is what I will reward. Okay? Okay, so let's continue on. Okay. State-based coverage. Okay. Now, having done this, there's many advantages. And in fact, compilers, as two of you may know here, Bernd and your name again? James. Bernd and James may know from the compiler course, compilers do this automatically. So when a compiler analyzes your Java code or your C code, it will construct a flow graph like this. In many cases for optimization, amongst other things. Optimization or even for instruction emitting in certain cases, particularly for more complex architectures. And it turns out that it can be really useful to kind of reason about the behavior of a system, among other things to reason about register allocation, etc. Okay, so we could do so there. We can also do so with more high-level diagrams, such as these here, and reason about what things would allow us to achieve coverage here in terms of these transitions. Now, it could be, I will note, and I thought I had it here, but the colors aren't showing up well here, and I'm concerned about that. Yes, here. Okay, good. So here's some coverage. We might try to achieve state coverage in a diagram like this by heading between states with two abstract paths. But one key thing to realize is that abstract paths, you can fool yourself. You can have an abstract class, you say A, B, G, and you don't realize there's a contradiction, that it's not in fact possible. You can get into cases where this is an infeasible situation that you cannot realize a given abstract class, in which case, given abstract path, in which case you have to go back, create another set of abstract paths, which recreate it, and try to find test cases for those. The point is, when we identify abstract paths through the diagram, we abstract away from conditions. And we may find later that the conditions, in fact, rule out realization of those paths. Okay? So just be aware that you can fool yourself. Okay, so state-based coverage is generally weak coverage. You can miss a lot of problems here. Let's take an example of this. There's a big testing gap associated with, particularly with low-level code, where it works fine in one path that covers the nodes, but fails on another path. And a classic example of this, a variable is left uninitialized, or a pointer or reference is uninitialized. Okay, this is getting truncated in an unseemly fashion. But here, we might have code that looks like this. And we achieve state coverage with one simple path here. What single path would achieve state coverage here? There's a line down here where we assign into phead, a value into phead. In other words, we dereference it with a star in front of it. So what's one path through this that would achieve a state coverage?
If it was true.
Okay, if it's true. So we go like this. Critically, in that one path, we have to cover this node, and then we reach here, right? That would achieve state coverage, right? Now, what obvious bug are we missing here?
What if foo isn't true?
Yeah, if foo is not true, then we have a bad situation because we have a null pointer exception. We assign through a null pointer. We're not going to turn that up with state-based coverage. It's going to blithely say, oh, we reached all statements, things are hunky-dory. And they're not. If we did transition coverage, we would need to do what? That would be stronger. With transition coverage, covering all the transitions here, what would we need to do? I said state-based coverage you could achieve without finding this bug. How about transition coverage?
Transition the false version of that.
Yeah, you would need to transition the false version. So this is the true. Another transition would be this is false and you fall through. And if you tested that in addition to the true one, you would find this bug. You would find this bug where it's false. So this is an example of a bug that could turn up if you engaged in transition-based coverage, but not if you engaged in state-based coverage alone. And in general, for each level of stronger coverage, you gain more in terms of confidence. You're covering it more thoroughly. So transition-based coverage, we're covering the edges in the graph. And there may be many test paths, abstract paths that cover a particular edge, but we need to cover it at least once, all right? And for each path, we have to find a particular situation that will extract it. This is a sort of coverage that was done as part of the Excel team when I was there for that core algorithm. And basically, you're making sure every single transition here is covered at least once. Okay. Good. Now, transition coverage is not perfect either. We haven't covered all combinations of conditions. We come in with this being true, when we leave with this being true, come in with this being true, this being false, this being false, this being true, and this being false, and this being false. We're not, with transition coverage, we're not testing all possible combinations. But at least we're testing the basics of transitions. And ladies and gentlemen, for this course, I will request of you come up in your test cases that you test transition level at a transition level for your diagrams at the high level. I'm not saying every algorithm. I'm not saying all your code. I'm saying that characterization at a high level of your code base for this reason that it's stronger. Okay, so here we have an if statement, and we need to go both this path and this path. With state coverage, we can do it just with doing like this. With transition coverage, we need to go both ways. Is that clear to people? People okay with that? Okay. Right. I don't think we have time to talk about this. Okay. For lower level coverage, we're using underlying knowledge of the code base in terms of knowledge of tests with nulls or testing of two variables equal to each other, testing the value of a variable, etc. And you're trying to figure out how to achieve certain goals. Sometimes this is fairly complex for the transitions. You may have an if statement whose result depends whether a hash table contained a certain value, and you're trying to come up with a test case that where that will be true. And so you have to figure out some way of doing it and running the program such that the hash table will have the requisite entry for you to trigger successfully that outcome. Okay, so it's not trivial to come up with these test cases, and occasionally you'll find you can't realize an abstract path, and you have to go back to the drawing board, come up with a different abstract path. Okay, good. So I would also like you, with an eye towards deliverables you give me, I want you to give me, for your projects, coverage reports. Typically, these will be by tools. Cobertura is a popular one. There's a number of coverage tools I listed, such as Istanbul. Cover.js, I think, is another one for JavaScript. I want you to give me coverage statistics for your code base. Okay. So you should be able to say, our tests currently cover 80% of our code base. Does this have to be done by ID2? No. I would like it for ID2. I do want to see the test cases that will exercise transition level coverage. For later IDs, I at least want to see some coverage coverage testing. And that includes statistics output by these tools. Okay? So please put an emphasis on that as well. Okay. Now, it turns out that these different levels of coverage have different levels of strength associated with them, and there's a subsumption relationship between them. It turns out that if you achieve edge coverage for a program where there's at least edges from or to all nodes, except the entry node, if you achieve edge coverage, you've achieved node coverage. If you've achieved edge pair coverage, possible pairs of edges, then you've achieved edge coverage. And it turns out that you can create a hierarchy of these. That's not necessarily, it's a partial order. It's not a complete order. Complete path coverage is the foremost. Can we achieve complete path coverage of a program? Consider a program, it's a user interface where the user interacts with it over time, maybe to drag items into it, or maybe to fill out items in a SCOGA, or to interact with it to allocate and deallocate bits. Can we achieve complete path coverage? Can we achieve all possible paths through the program? No. Plumb impossible. Just, among other things, the paths are of arbitrary length. You're not going to be able to execute the program for arbitrary amounts of time as part of this. So in general, it's not possible to test out all passable paths exhaustively. It's just out of the realm of possibility. It gets into the halting problem, for those familiar with that. So what we can do is often lower levels of this: node coverage, edge coverage, and prime path coverage. And alas, we're out of time. I may ask you to take a look at a video on prime path coverage, but I want you to provide me with edge coverage at the level of coming up with test cases for your system. And if you need help, glad to help. Ladies and gentlemen, have a wonderful break. I am here next week. I'd be most pleased to meet with teams and to talk and provide further advice. We may get you a bit more comments on projects, but good luck. Make use of the time. The vacation time, the break goes very quickly, and you'll quickly have to face the next deliverable. So if you can, make use of this next week nonetheless. Okay? Thank you very much.